All right, today we're going to dive into a really fundamental challenge in histopathology. We're talking about how you get a clean, beautiful, readable slide from something as tough as a piece of bone. And to do that, we have to master a truly essential technique, decalcification.
So here's the big question, right? Picture this. You're a histotech, and you get a sample, maybe a bone biopsy. It's hard, it's dense, it's packed with calcium. How in the world are you supposed to get a slice of that thin enough to see through on a microscope slide? That's the core problem we're going to solve today. How do you section the unsectionable?
So here's our game plan. We'll start with the why and when. Then we'll compare the different methods out there. We'll talk about how to perfect your technique, and maybe most importantly, how to know when you've hit the endpoint. After that, we'll cover post-decalcification steps and troubleshooting, and we'll finish up with some specialized bone processing. Let's jump in.
Okay, let's start at the very beginning. What exactly is it that makes decalcification a special technique, and when is it the right tool for the job?
You can think of your standard lab workflow, the whole fix, process, embed, section routine, as the main highway. A special technique is any procedure that's a necessary detour off that highway. Decalcification is a perfect example. It's an extra step that happens after fixation, but before you put the tissue on the processor. Another big one is frozen sectioning. That's a whole different route you take when speed is everything, like when a surgeon is waiting for a rapid diagnosis.
The whole point of decalcification is pretty simple. Get the calcium out so you can actually cut the tissue. This is obviously mandatory for bone, but also for any other tissues that have calcified for pathological reasons. Now, there are times you'd skip it, specifically for things like metabolic bone disease studies, where you actually need to see the calcium. Those cases are different. They require embedding in a hard plastic, not wax. And I want you to really focus on this last point because it is the #1 most important rule. Your tissue has to be fully fixed before a single drop of decalcifying agent touches it. If it's not, the acid will just eat away at the unfixed proteins, destroying the cell details and making your sample completely useless.
Okay, so now that we know why we're doing this, let's get into the how. There are quite a few different ways to get calcium out of tissue, and each one has its own set of pros and cons.
So at a high level, you can really group these methods into 4 main categories. First, you have your acid methods. These are the workhorses of the lab. They're fast, they're effective, but you have to be careful because they can be a bit harsh. Then you've got the ion exchange method, which is much more gentle and gives you fantastic staining for high-quality diagnostic work. The electrolytic method is blazing fast, but it's pretty rare these days because it can really damage the tissue. And finally, you have chelating agents, like EDTA. These are incredibly gentle, but also incredibly slow, so they're usually saved for special research applications.
Now, let's dive a little deeper into those acids, because there's always this trade-off between speed and preservation. Think of hydrochloric and nitric acid as the speed demons. They're super fast, but that speed comes at a price. They can be rough on the tissue. Nitric acid can actually start causing damage in just 48 hours. Formic acid, on the other hand, is the gentler option. It's slower, for sure, but the tissue holds up much better and you get better staining in the end. You can even find mixes that have both formic acid and formaldehyde, so you can fix and decalcify at the same time. Oh, and a huge safety note for hydrochloric acid. You absolutely must wash all the formaldehyde out of the tissue first. If you don't, they can react and form a nasty carcinogen called bischloromethyl ester. It is just not a risk worth taking.
Okay, this is where things get really clever. The ion exchange method is so elegant. It uses formic acid just like the other methods, but you add a layer of a special sulfonated resin to the bottom of the container. So as the calcium ions leave the tissue, they get immediately snatched up by this resin. In exchange, the resin releases ammonium ions. What this does is it keeps the formic acid solution from ever getting saturated with calcium. This keeps the reaction going strong and protects the tissue from sitting in a soup of its own dissolved minerals. The results are just beautiful staining, and you don't have to change the solution nearly as often. It's widely considered one of the absolute best methods for diagnostic quality.
Now let's look at 2 methods that are complete opposites. On one side, you have the electrolytic method. This is pure brute force. You use an electric current to literally pull the calcium ions out of the tissue towards a negative electrode. It's incredibly fast. We're talking 2 to 6 hours. But the heat it generates can literally cook the tissue, which results in terrible staining. Then on the other end of the spectrum, you have EDTA. It's what's called a chelating agent. Think of it like a tiny molecular claw that gently grabs onto individual calcium ions and plucks them out of the tissue. It is super, super slow, but the tissue preservation is just second to none. That makes it perfect for really delicate things like enzyme histochemistry. So we've covered the different methods. Now let's talk about the hands-on part. How do you actually do this in a way that gives you the best possible results, both safely and efficiently?
If you want to get the best results with acids, you can't just set it and forget it. You've got to manage the process. First, change the solution often. This stops it from getting saturated with calcium, which would just stall everything. Second, agitation helps keep fresh acid right up against the tissue surface. Third, using a vacuum can really help pull the acid deep into dense bone, and it also removes tiny gas bubbles that can block the acid. Fourth, using an embedding bag stops the tissue from just sitting on the bottom of the container, so all the surfaces get evenly exposed. And finally, if you're using a fast-acting acid, you have to monitor it like a hawk. It's your only defense against going too far and ruining the sample.
Okay, I absolutely cannot say this enough. Never, ever apply heat to speed up decalcification. It might seem tempting, like a quick shortcut, but the acid reaction will just go wild. You will literally cook and digest your tissue. It causes irreversible swelling and maceration, and it completely destroys the morphology. There is no coming back from that kind of damage. And of course, working with strong acids means safety is absolutely non-negotiable. Your PPE, a protective apron, gloves, and eye protection is your first line of defense. Always work in a fume hood to protect yourself from corrosive fumes. Store acids in the right carriers to prevent spills. And remember the golden rule you learned in chemistry. Always add acid to water, never the other way around. It prevents a violent reaction that can splosh acid everywhere. And finally, when you're done, neutralize the waste with 1% sodium bicarbonate before you pour it down the drain. It protects our pipes and the environment. This next part, this is absolutely critical. Knowing when to start the process is one thing, but knowing exactly when to stop is just as important, if not more so. You are walking a very fine line here. If you stop too early, the tissue is under-decalcified. It'll be hard, it'll feel gritty, and it will absolutely shred your microtome blade. But if you go too long, it becomes over-decalcified. The tissue gets soft and mushy, and even worse, you get terrible nuclear staining. The acid actually starts to break down the DNA, so can't pick up the hematoxylin stain properly. You end up with these pale, ghost-like nuclei, and that makes a diagnosis almost impossible.
So how do you find that perfect Goldilocks zone? Well, you've got three main ways to check. The mechanical method, bending it or poking it with a needle, is the least accurate because it's just so subjective. Plus, you can easily create artifacts that might look like pathology. The chemical test is much more accurate, and it doesn't damage the tissue. And then you have the radiographic method, which is basically taking an X-ray. It's the most accurate method by far. The only catch is that you can't use it if you used a fixative that contains metal, like zinc or mercury, because those will show up on the X-ray and block you from seeing the calcium.
Let's actually walk through that chemical test because it's a really neat bit of chemistry. You start by taking 5 milliliters of the used decalcifying fluid. Next, you neutralize that acid with some concentrated ammonium hydroxide. Then, you add 5 milliliters of saturated ammonium oxalate. Now, if there is any calcium left in that fluid, it will react with the oxalate and form calcium oxalate, which is a white solid. That's what makes the solution look cloudy or turbid. If you let it sit for 30 minutes and it's still perfectly clear, that means there's no more calcium coming out of the bone. You've hit your endpoint.
Okay, you did it. You successfully hit the endpoint, but you're not quite at the finish line yet. Let's go over the final steps and talk about what to do when things don't go as planned.
So once the decalcification is officially done, you have to wash the tissue really well. Usually this is done in running water to get rid of all that leftover acid, which could mess up later processing and staining steps. Some labs also do an optional neutralization step with something alkaline, like lithium carbonate. This is also the perfect time to do your final trimming to get the specimen to the right size for the cassette. And here's a pro tip. For really large bones, using a diamond saw to cut them into thinner slabs before you even start the process can save you a huge amount of time, just because the acid has less tissue to penetrate.
Let's quickly run through the 3 most common headaches you might run into. First, bone dust. If you use a regular saw, dust can get pushed into the tissue and create artifacts. The best way to prevent this is to use a diamond saw or to just carefully trim the surfaces of the bone after you're done decalcifying. Second, underdecalcification. This usually happens when there's a rush for a fast turnaround. The key here is to pick a fast-acting agent from the start and use a reliable endpoint test like radiography. And third, overdecalcification. This is almost always caused by just not monitoring the endpoint closely enough. Prevention is really the only cure. Pick the right agent for the job and be super strict with your endpoint checks.
And really, All this troubleshooting, all this technique, it all comes back to one simple, powerful idea. It's so easy to get obsessed with turnaround time, but at the end of the day, a quick slide is absolutely useless if it's unreadable. The diagnostic quality of that slide is everything.
All right, to wrap things up, let's just touch on two pretty specialized scenarios. What to do when you intentionally don't want to decalcify a bone, and how to rescue a block when you find unexpected calcium on the microtome.
So let's look at these two advanced approaches. First, undecalcified bone processing. This is for when you're studying something like metabolic disease and you need to see the calcium exactly where it is. To do this, you have to ditch paraffin wax completely and embed the bone in a super hard plastic like glycol methylacrylate, or GMA. Or you can physically grind the bone down into a section that's about 75 to 100 micrometers thick. The other scenario is a rescue mission called surface decalcification. This is for when you're cutting a block and you unexpectedly hit a patch of calcium. You can take the block off the microtome, apply a drop of 1% hydrochloric acid to the face for about 30 to 60 minutes, and it will soften just that very top layer enough for you to get a few usable sections. It's a real last-ditch effort, but sometimes it can save the case. And that really brings us full circle. From powerful acids to gentle chelators, from careful planning to last-minute rescues, mastering decalcification is all about knowing which tool to use to deliver the absolute best slide possible.